doing actual mathematics. Perfect. Only 7 minutes short. All right. So we're going to say that we're going to leave the port at Boston. So here's Boston at a bearing of south 80 degrees east. So I'm going to say here's south, north, west, and east. And south 80 degrees east is off in that direction, where this whole bearing takes me 80 degrees to the east of south. So again, starting from due south, here's due south. I'm going to go 80 degrees to the east. So south 80 degrees east is from the south 80 degrees to the east. After an hour, the ship turns 90 degrees towards the southwest. So 90 degrees towards the southwest. 90 degrees. And 2 hours at an average speed. So let's see. Here we went 10 knots in 1 hour. So we went 10 nautical miles. Richard says we only see grid paper. It's working, right, Richard? You're seeing the problem? I think so. I can see it. My user view. Yeah, it's fine. It's fine. Yeah, cool, cool, cool. Okay, good. 10 miles we went, and then now we're going to go. So we went 1 hour at 10 knots. Now we're going to go 2 hours at 20 knots. So 2 hours at 20 knots is going to take us 40 miles. And we want to know now what's the bearing of the ship from Boston. So in order to find that out, I know that with one side and another side, and we're going to connect from Boston, I'm going to make a triangle. And I want to say, okay, what are the angles in this triangle? So I'm going to say, okay, to find the angles in the triangle, I'm going to ask tangent of what angle has a ratio of opposite side 40, adjacent side 10. So then I'm going to say theta equals the inverse tangent of 4. And coming over to a calculator, inverse tangent of 4 76 degrees. $75.96 degrees. Okay, so we know, zooming in here, that the ship came almost back so that it would be due south. Really close, not quite, but really close. And going 40 miles, it came really close to back to due south, just 5 degrees short of that. So here we are. Our connecting line goes like that. And our angle here is 75.96 degrees. And now, for the port at Boston is trying to reach our ship. And the port at Boston wants to know, what's this little small angle, theta? Owen says, wouldn't the tangent of theta be 10 over 40? We could certainly do tangent of theta 10 over 40, and we'd just find a different angle. I was finding this angle here. I found this angle as theta, and so I used opposite side 40, adjacent side 10. You certainly could find this angle down here and use opposite side 10, adjacent 40. Does that make sense, Owen? Hopefully. Anyway, in order to find my bearing angle, I'm going to do 80 minus 75.96. So I'm going to come over here and say, what is 80 minus that? And I get 4.03 degrees. And so this angle, theta, is, oh, I used theta already. Maybe I should use a different angle. How about this angle, alpha, equals 4.03 degrees. And so the bearing for Boston to reach the ship is now south 4.03 degrees east. Yeah, got you. No problem. Any other questions on that bearing problem that I gave you for review? No, pretty good. Should we start back at the beginning? For your quiz problem. What do you mean by that, Richard? Beginning. Yeah, beginning sounds good. I'm not sure what you're saying, Richard. North 4.03 degrees west. To go back to the original point. Oh, yeah, like the quiz, if you wanted to go back to the original point, excellent. Yeah, it would be north 4.03 degrees west, totally. If it was the boat trying to get back to the original point, excellent. Well said. Exactly correct. Yeah, so this was Boston trying to reach the boat, so it was north 4.03 east. If it was the boat trying to get back to Boston, it would be north 4.03 west. Cool. Okay, let's go back to the beginning. So we started with number 2. Oh, there's where I put that. Cool. Number 2, find the exact value of the 6 trigonometric functions of that angle with base 3 and height 5. Okay, new page, new photo, zoom in. Okie doke. So the 6 trigonometric functions are sine of theta, cosine of theta, tangent of theta. I'm going to do cosecant of theta, secant of theta, and cotangent of theta. And right away, looking at sine of theta, I know sine of theta is the opposite side over the hypotenuse. And I can see that I'm missing the hypotenuse. I need to know it. So I'm going to say over here that 3 squared plus 5 squared equals c squared, and 9 plus 25 equals c squared, and 34 equals c squared. So c equals the square root of 34. Cool. And I'm going to say that means that the opposite side over the hypotenuse will be 3 over root 34, which equals 3 root 34 over 34. Does anyone want me to show getting from this step here to this step here? Or is that fine? Let's see, Richard, we are not using radians. Are you talking about radical measure? And no, you should definitely use radical measure. You should definitely use radical notation here. Radians is going to be something that's big next quarter. We're going to totally get into radians pretty deep. Right now, we haven't done radians at all, but we will. But for this answer, you should definitely be doing radical notation, not approximating your answers. Cool. Brennan says it's cool, so it must be cool. On to cosine. Cosine of theta is the adjacent over the hypotenuse, which is adjacent side 5 over hypotenuse root 34, which equals 5 root 34 over 34. Sweet. That was cosine. Tangent is the opposite over the adjacent. Which equals the opposite side 3 over the adjacent 5. The cosecant of theta is the inverse of sine. Or sorry, the reciprocal of sine. So it's the hypotenuse over the opposite. And it is root 34 over 3. And the secant of theta is the reciprocal of the cosine. So it is hypotenuse over adjacent. And it is root 34 over 5. And lastly, the cotangent of theta is the reciprocal of tangent and also its cofunction. So it is the tangent of the complementary angle, which is adjacent. That wasn't a very nice A. Adjacent over opposite 5 over 3. Sweet. Old stuff. We remember it? We need any questions on it? We feel good? Cool. I feel good. Let's move on. Oh, Richard says, oh, got you. R, thumbs up. I love it. Great. Okay. We did 6. Oh, no, we did 2. Let's talk about 6. Cofunctions of complementary angles. Tan 15 minus cotangent of 75. Tangent of 15 minus cotangent of 75. This is problem 6. And we want to deal with this without a calculator. So we don't want to plug in tan 15 or cotangent of 75, but we do want to say, what does this look like? Hey, Richard, this is a good test question. Pay attention. So I've got 15 and I've got 75. And I'm going to name my sides side A, side B, and side C. And I'm going to show that tan of 15 would be the opposite side over the adjacent to 15. So that's going to be opposite A over adjacent B, A over B. Minus cotangent of 75 is the adjacent side over the opposite of 75. So adjacent to 75 is A, and opposite 75 is B. So A over B. And what is A over B minus A over B? Wait, you weren't laughing, Emily? You didn't catch my awesome joke? Math is hilarious. Everyone was having fun. Okay, A over B minus A over B is 0. Thank you, guys. Much appreciated. Excellent. Now, Emily, I just accidentally left it as comedy. It's the default setting when you make a new one of these things on YouTube. And then I realized it afterwards, but you can't change it once you set it up. And I'd already emailed out the link. That's why. Great. That was number 6. Should we do number 12? Good. I'm glad to hear it, Brendan. Any questions on 6 before we go on to 12? Great. 12. We've got this one. Let's get it out by itself. We want to solve the triangle. Okay, so solving this triangle, let's see. I need to find side B, I need to find side C, and I need to find angle B. So I'm going to say I need side B, I need side C, and I need angle B. My first step is going to be to go ahead and find angle B. So I've got 90 degrees plus 35 degrees plus angle B. I know that a triangle has a sum. Richard said, for the last question, why can we not use our calculator? Oh, well, I mean, on a test, Richard, if hypothetically you had to explain why sine 15 or why cotangent of 15 minus tan of 75 equaled 0, then just saying I put it in my calculator and they equaled 0 would be a pretty poor explanation, and you would get very minimal credit. Does that make sense? Hopefully.
Yeah, exactly. You want to be actually able to draw the triangle and then articulate an explanation of the fact that co-functions of complementary angles mean it's the same function for the complementary angle because you have the opposite side switched with the adjacent side. You would want to be able to articulate that in a full and complete manner, which just saying I used my calculator wouldn't do. Yeah.
All right. 90 degrees plus 35 degrees plus angle B is all going to add up to 180 degrees. So 90 and 35, 125 degrees. So angle B, I'm going to be pretty committed, is equal to 55 degrees. Sweet. Now I have side B. I'm going to go ahead and find side B next. So in order to find side B, I'm going to use my 35-degree angle and my opposite side 5, and B is adjacent to 35. So I'm going to use my tangent ratio. So I'm going to say the tangent of 35 degrees is equal to the opposite side 5 over the adjacent side. And I want to solve this for B. So I'm going to say B equals 5 over tangent of 35 degrees. And I'm going to go ahead and pull out a calculator. And 5 over tan 35, 7.14. Cool. And C equals. And here I could use Pythagorean theorem. Be a great way to do it. I'm going to go ahead and use another trig ratio because I can not have to make use of a previously approximated value. But there's lots of ways to do it. I'm not going to dock you for using an approximated value. It's fine. Just a good strategy would be to avoid it. So I'm going to go ahead and say, all right, using my 35 degrees, I know that the opposite is 5, and I want the hypotenuse. So I'm going to go ahead and rely on my sine ratio. The sine of 35 degrees is equal to the opposite side 5 over the hypotenuse C, which means C equals 5 over sine 35. And 5 over sine 35 is 8.7. C equals 8.7. 2. Rockin'. Any questions on that one? My computer says there's 25 of you watching. Only like 3 or 4 of you are ever talking. Can the rest of you like hear and see all right? I hope. All right, number 20. We've got an angle side problem. Or sorry, a side angle problem. Richard speaks for us all. Got it. There's no need for anyone else. Thanks, Sophia. Now I understand. Okay, so we have A equals 3, C equals 1, and angle C equals 20. Number 20. A equals 3, C equals 1, angle C equals 20 degrees. Okay, well, you're lucky. You're all lucky to have Richard, I suppose. So let's see. I'm using the law of sines. I'm keeping in mind that this is a potentially ambiguous case. I have two sides and an angle. I want to watch out for the possibility of multiple triangles in this situation. Of course, who isn't? Okay. So I'm going to say, let's see, sine of 20 degrees over the opposite side 1 is equal to the sine of angle A over its opposite side 3. Meaning that sine of angle A equals 3 sine 20. So delete my problems from last time. 3 sine 20. 3 sine 20 is 1.02, 1.03. And I'm already thinking to myself, this is odd. The sine of some angle is 1.03. How is it possible that the opposite side is greater than the hypotenuse and this ratio is greater than 1? Richard, I cannot set up a triangle because there is no such triangle. It's impossible. Because when I try to do inverse sine, of 3 sine 20, undefined, error, problems, not possible. Got it. It is comedy, right? Thank you. Excellent. Good joke. No triangle. If I wanted, though, to think about what does this look like, I think it's worth doing. If I have C equals 1 down here, and I have A equals 3 somewhere, A equals 3, and then I have this angle of 20 degrees. There's my side, and there's my side, and there's my angle. And they're just not going to reach. Just not going to work. Just not going to come together. No triangle. Too far away. Can't be met. Any questions on no triangle at number 20? Ambiguous case? You run into problems? That's a really interesting mix of English, slang, Spanish, and chat. Thank you, Brennan. Anyway, let's move on to 20. Let's see. We got, after 20, we did 30. On number 30, we had 3 sides. Great. Beautiful case of the law of cosines. A equals 3, B equals 2, and C equals 2. Okay. 3, 2, 2. And we want to find angle A, angle B, and angle C. So in order to do this with the law of cosines, we're going to say, let's go ahead and work with, I'm going to start with angle A. So A squared equals B squared plus C squared minus 2 BC cosine of angle A, which means 3 squared equals 2 squared plus 2 squared minus 2 times 2 times 2 times cosine of angle A. And 9 equals 4, 8 minus 2 times 2 is 4, 8 sine A. And we've got 1 equals negative 8 cosine A. And cosine of angle A equals negative 1/8. And angle A is the inverse cosine of negative 1/8. Inverse cosine of negative 1/8. 97.18 degrees. Emily says what chapters are on the midterm. Lauren says chapter 8. That's correct. Emily says what lessons, or just the entire chapter. Lauren, 8.1 through 8.5. Colby agrees, but except for 8.5. And Richard says, how did O2 get negative 1? Let's see. Colby, you were correct. It is everything except for 8.5. We did not talk about dampened harmonic motion or simple harmonic motion. And Richard, I don't know what you mean. Oh, how did I get negative 1? I didn't get negative 1. I did get 9, and then I got positive 1. And then when I divided positive 1 by negative 8, I got negative 1/8, because a positive divided by a negative made a negative. Is that what you mean? Oh, inverse cosine. Cosine to the negative 1. Yes, that is inverse cosine. We could write it arc cosine. Would that make it better? We could say this was arc cosine of negative 1/8. Desmos even knows what that means. Arc cosine of negative 1/8. Cool. Angle A, 97.18 degrees. And let's see. What are my options now? Let's hear from you guys. Gotcha. What do you guys think we should do next? Well, first, I appreciate Lauren and Jake and Shemaya, who actually talked about how to finish the problem, rather than the rest of you who are just like, all right, he's got one angle, let's move on. We can certainly do that. Oh, was I chewing too loud? I thought I put my microphone down. Sorry, Richard, my bad. Let's see. So, yeah. I could certainly do law of sines. I could certainly do another law of cosines. Could do sine to get the other angles. I'm with Jacob, though. It's an isosceles triangle. I'd rather just take the remaining angles and divide by 2, right? I know it's got to add up to 180, and I know the remaining angles are the same, so I can just find the rest of it and divide by 2. Does that make sense? Yeah, so I could do that, like Oscar said. I could do law of sines. It's a great way. It's not bad at all. I'm going to go ahead and just point out that since this triangle is isosceles, 2 and 2, this angle is the same as this angle. So I can just say, all right, we got 180 minus this. So the rest of the angles have to add up to 82. And since they're isosceles, I can just divide that by 2, and each one's going to be 41.4. Yeah, I get you. Excellent. Now, just because it's worthwhile to do some practice, let's go ahead and do a law of sines problem as the next step. So if I was going to do law of sines, maybe I don't notice that it's isosceles, or I've forgotten the isosceles-based angles, which you guys would never do. But just in case, I've got angle A. Now I want to find angle C, so I'm going to say sine of 97.183 equals sine of angle C over 2, which means that the sine of angle C equals 2 sine of 97.18 over 3. And I would use inverse sine. Let's go ahead and plug that in for now. So I've got 97.18. I'm going to say 2 sine of 97.18 all over 3.66. Sophia says, question, are you chewing with your mouth open? Owen says, is the same angle a property of isosceles triangles? Yes, Owen, to your relevant question, the same angle as a property of isosceles triangles. And the rest of you all ignore. So sine C equals 2 sine 97.18 over 3. We got that. Sine C equals 0.66. I'm going to take inverse sine to get C. Inverse sine of this whole mess. Uh, 41.4. Hey, just like we said when we looked at isosceles triangles. Perfect. Angle C, back to our diagram, 41.4 degrees. And the other angle, we can hopefully figure out now. At least we've got 2 angles. The last one's going to make 180. So 41.4. Any questions? Relevant to the topic of learning math, Sophia? Cool. Brad, let's move on. Let's see. We did 30. We want 42. Or did you guys want to go on to, you guys, when we asked about what we should do next, a lot of you wanted to talk about, Colby says, why can't we just use Desmos on the test? That's a good question. So Colby, one thing is, at this point, I only know how to set up
Desmos on for testing use on an iPhone. I can't. So on an iPhone, I can just like lock you into Desmos, and you can't get out without my code. So I don't. That's perfectly fine for a test. But if you have like an Android phone, I don't know how to do that. I think there will be some tests where we will just go ahead and use Desmos. I'm worried about making it possible for this test because I'm worried there will be some people who don't have an iPhone but would like to use Desmos. But I can go ahead and ask. I'm happy to ask at the beginning of our class and say, okay, is it all right if those people who want Desmos and there's an iPhone available use Desmos? Does that sound good, Colby? There's a bit of a lag between when I say something and when you guys actually hear it. Sophia says always. Anyway, yeah, I can go ahead and ask and check that out because I can let you use Desmos if you have an iPhone. I have no problem with that on this test. There are other tests where we can't really, like when we get to graphing next quarter, then I'm going to have some things where it is graphing calculator available and other things where you have to do the graphing by hand. Yeah.
Well, let's go ahead and move on to, we did 30, 42. 42 is our last, oh, that's our Heron's Law problem. Pretty straightforward. Did anyone need 42? Should we just skip that one? That one was really easy, right? Just plug in Heron's Law. Should we skip that and go on 56 and 60, some of the word problems? Oscar says, did we get a handout on the ambiguous case? I don't think we got a handout. I think we just got notes. Oh, Ryan says, yes, we did. Oh, I'm not sure if he's replying to Oscar. Maybe he's just replying to me. That's cool. Okay, let's do that. 56. Correcting a navigational error. I love this problem. Let's see. A sailboat leaves St. Thomas bound for an island in the British West Indies. How colonial. 200 miles away. Maintaining a constant speed of 18 miles per hour, but encountering heavy crosswinds and strong currents, the crew finds, after 4 hours, that the sailboat is off course by 15 degrees. Oh no. How far is the sailboat from the island at this time? Lauren says we had a book assignment for it, I think. Ryan says no. Yes to your question. Ryan says, yeah, we took notes on ambiguous case. Agreed. Cool. All right. A, how far is the sailboat from the island? So the first question they're asking is X. How far is that? And we've got 15 degrees. And we know that they went constant speed of 18 miles per hour for 4 hours. So constant speed, 18 miles per hour times 4 hours equals what? 72? 70. Oh, that doesn't show up very well. 72 miles. And they were 15 degrees off. So this is a pretty straightforward case of the law of cosines in order to find side x. So I'm going to say that in this case, because I know that c squared equals a squared plus b squared minus 2ab cosine of c, that x squared is going to equal 72 squared plus 200 squared minus 2 times 72 times 200 times the cosine of 15, which means, well, heck, I'm just going to go, I'm with Colby. Desmos is nice. I'm going to go over to Desmos and say x squared equals 72 squared plus 200 squared minus 2 times 72 times 200 cosine of 15. Great. Sherman degree mode, I am good. So 131.776 is this distance from the sailboat to the British West Indies. 131.78 miles. Hi. Let's see. Next up, 131.78. Through what angle should the sailboat turn to correct its course? So now I need to know, okay, they want me to tell them what angle is here. In order to get that, I'm going to need to find this angle here. So I want to find theta in order to get this angle. How about theta?
Wait, some kid who's not in pre-calculus is watching our video? That's awesome. Yeah. You're going to have so much fun. Just ask these guys. It'll be great.
So let's see. I know angle. I know side. I know side. I know side. So I'm going to go ahead and say, given the side I just found, and this side, I'm going to use law of sines to find angle theta. So sine of theta over 200 is equal to sine of 15 degrees over 131.78.
Yeah, thank you, Richard. Oscar's being depressed is not my fault.
Let's see, sine of theta. So sine of theta equals 200 sine 15 over 131.78. So sine of theta, 200 sine 15 over, and I have it in here so I can just say x. No, I can't. But I think if I make this a better variable, like maybe c, I'll just be able to use it down here, c. Nope, still doesn't like it. Okay, fine. 131.78. So sine of theta
it's back to normal. Yeah, we're good. Right, Oscar? Oscar says buffer. Oh, buffer. Is it me or is it buffering? Got it. Back to normal. I think so. I think we're fair.
Okay, sine of theta equals 0.39. So inverse sine of all of this. $23.13.
Sorry, kid. No can do. Not at the moment, at least. Come to my room and I'd be happy to help you. Okay, but now we got problems. What's my problem? Does anyone see my problem? What's happening here? What's the problem with theta being 23.13 degrees? Ambiguous case. Thank you, Sonny. Wonderful. No bearings in this problem. Sonny is right.
Excellent. I'm looking at an obtuse angle. Everyone can see it. Really obtuse. Very obtuse. I just found this angle, the supplement of the obtuse angle I want. So this angle I haven't found. It's obtuse, but guess what? This is the angle I need. The supplement to theta is beta, and I just happen to find beta. What? Okay. So I did a law of sines problem. Ryan used law of cosines to avoid the problem, but see, Ryan, I knew that law of sines was going to find me the acute supplement, and I knew I wanted the acute supplement, so I used law of sines because it's actually shorter than using law of cosines, and I actually need to subtract it from 180. Yeah, right? This is just geometry. Thank you, kid. Because this is exciting, Oscar. Okay, but I'm guessing I probably lost some people on that. So I'm gonna back up. I'm gonna say, okay, I'm using law of sines. I don't realize that I have what I need. What should I do instead? So I'm gonna say, okay, sine of theta, 23.13. It's not possible that this angle theta is 23.13 degrees. So I really want to find theta. I'm going to say that the actual theta is equal to 180 minus 23.13. So I'm going to go ahead and do 180 minus all this. 156.87. So I'm going to zoom in here and say, okay, now I've found theta. It's 156.87. Now the angle that I need to turn by is this angle. That's the turn that the boat needs to make to the left. That's this angle over here. In order to get that, I'm going to do 180 minus 156.87. So this equals 156.87. Now to get beta, it's 180 minus 156.87 equals 23.1 degrees. Emily says, is that because you can't use law of... Yeah, law of sines is never going to give you as an output an obtuse angle. Exactly correct. Is that what you're asking me, Emily?
I think so.
Okay, so 23.1 degrees. I just found beta, and that's my answer. Ryan is absolutely correct. If you want to avoid the ambiguity of dealing with this ambiguous case of the law of sines and having to recognize obtuse and acute angles and what you need when, you are safer with the law of cosines. So the law of cosines would have told me right away that theta was 156.87. And then I would have gotten beta 23.1. But they both work. So I have my answer here to part B, 23.1 degrees. And I'm assuming that the speed remains 18 miles per hour. So let's see. The trip with no error can't spell error would have been 200 miles times 18 miles per hour, which would be 3,600 hours. Let's see. Divide that by 24. So 150 days they would have been at sea. Is that right? Oh, no, I'm dividing. Whoa, that's all a problem. 200 miles divided by 18 miles per hour. That's better. That makes more sense. So it would have been 11.11 hours. And now I want to know, okay, at their current method, it's going to be 72 miles. 72 miles plus another 131.78 miles. So with error, it's going to be 203.78 miles over 18 miles per hour. Thank you. Algebra 1 caught my mistake. Not divide, exactly. 203, So divide all this by their speed of 18 miles per hour. 18 miles per hour, 11.32 hours. So this minus 218ths is, it's going to take them 0.21 hours more. That's a weird way to phrase that. So I'm going to multiply that by, let's see, there's 60 minutes in an hour. So 12.6 minutes more. 12.6 minutes due to their mistake. Every time someone says divide, it highlights Richard. That's awesome. And thank you, Oscar. You got my mistake. Much appreciated. Cool. That was 56. Any questions on 56? How did I get 203.78? Well, to get 203.78, you can see over here in the Desmos, I did, oh, you can't see my, yeah, I did 72 miles plus 131.78. So here it was. This is their journey with the mistake. They would have been 200, but with the mistake, they're 72, 131.78. Drawing's not very nice, but that's the right answer. Oh, thank you. Algebra 2. Did I say algebra 1? My bad. 72, 131.78. Good, Richard? Good. Good. Okay, cool. That was 56. We did 60 to start the problem because it was bearings. We have nothing left but 61, and it's only been an hour. Check us out. So we'll probably have time to, let's see, talk about comparing and contrasting law of cosines, law of sines, and Heron's law. Right? That was something we wanted to do? Should we do 61? Let's do that. 61. Drive wheels on an engine. Yep, let's do all the problems and then the compare and contrast. Brilliant, sounds good. It's a plan. Okay, so the drive wheel of an engine is 13 inches in diameter. And the pulley on the rotary pump is 5 inches in diameter. Drive wheel, 13 in diameter. Pulley, 5. Shafts of the drive wheel and the pulley are 2 feet apart. What length of belt is required to join them as shown in the picture? Great problem. Love it. So we got side length that we know is 2. This distance we don't know, but we can see it's the same as this distance. And then we need this and this. Oscar says we suck. I don't know why that's true, Oscar. So I'm going to go ahead and add to my diagram there. And let's see. I'm going to say we need to find this length, x, which is the same as this length, x. And then I'm going to have to find this length, which is a half of a circle, and this length, which is also a half of a circle. And let's see, how am I going to find this distance, knowing 2 feet, 6.5, and 90? Any ideas? Let's go ahead and find the half circles first, and you guys can think about what do we do with x, because that's the tricky part. So let's see. Circumference of a circle equals 2 pi r. C equals 2 pi times the radius. In the big circle, I have C equals, let's see, and I only want half a circle, so I'm going to go ahead and say divide it by 2. This half circumference equals just pi times the radius. And our radius is 6.5. So our half circumference equals pi times 6.5. So this half circle equals 6.5 pi feet. And this half circle over here equals 2.5 pi feet. Brennan says use the 90 degrees things to get x some way, somehow. I agree. 90 degrees is going to be important. Emily says this is similar to another problem we've done. I believe that. That makes sense. Okay, so I'm going to summarize our work so far by saying we've got this half circle and this half circle and 2 x's. So we know that our total belt length so far is equal to 6 and 8, 9 pi feet plus 2x feet. So now we really need to focus on x. Richard, is this going to be on the test? It's possible. Okay, so zooming in here on x, what can we do with x? I think Emily is remembering a trig star problem in which there was 2 right angles. What do we have to do in that problem? Split the parallelogram in half. I love it, Oscar. That's such a brilliant plan. Let's do that. Let's split the parallelogram into half. It's not actually a parallelogram, though. Oh, no, it is parallelogram. Oh, no, it's trapezoid. Trapezoid in half. So I've got half a trapezoid and half a trapezoid. Oh, I don't want an arrow. I want a line. So there's half over there and half like that. That's going to be important. And there's a line over here. And that's going to be important. Okay, so we want x. We know 6.5 and 2.5. And Emily says you could also find the opposite 2 angles. How am I going to find the opposite 2 angles, Emily? Can we form 2 triangles? That's what we're doing. Yeah, we're forming a few triangles. Okay, so I'm going to start working. Let's see, I'm going to change that from red. I'd like that to be blue so I can see the difference between my 2 triangles. Or actually, blue blends in purple. And I'm going to start by leaving this purple out. I'm going to say just here in the red triangle, I have, or sorry, just here in the top half triangle, I have a right triangle with length x and 6.5. So that's a right triangle that I know one side of. And over here, I know 2, and actually I know 2 sides over here. Never mind. Oh, cool. And when I add in this purple one, I've got, let's see, here's a right triangle in which I know 1 side, 2 sides, and here I know 1 side, 2 sides. Okay. And I'm going to start naming these angles. I'm going to name my angles in green, and I'm going to say angle 1, angle 2, and angle 3, and angle 4, and angle 5, and angle 6, and angle 7, and angle 8. Just take, nice, Richard. No, this is harder than I think I would put on a test. I don't think I would do the problem this hard on a test. It's tricky. It was the only tricky one I gave you, though. Okay, so I'm gonna do this move. I'm gonna back up and give myself a little more room with a blank space. So we've done some good work here, and now I need to see it from a different perspective. So I'm going to go blank and pull the problem back up. Okay, so something I'm going to need to add. I like the idea of splitting in half, but here's what else I want to do. The split in half was good. I want to extend my problem. And I'm going to extend it there and there. That gives me a little more triangle information. And now, see, I get two triangles. I get a little triangle over here and a bigger triangle here. And what kind of triangles are they? Similar triangles. Thank you, Ryan. I love it. So let's see. I know 2 feet. So out here to this is 6.5 feet. And out here to this, that's 2.5 feet. So that's 9 feet altogether, or 9 inches. Let's see. From here to here, how long is that? Ryan says now we can use ratios. Brilliant plan. How long is this side here, this little green bit? I think it's, let's see, 9 inches. If my whole 2 feet, how many inches is 2 feet? I think that's 18 inches. So with my 9 inches, this would be 9 inches, right? No, 2 feet is 24 inches, my fault. 2 feet, 24 inches, and Richard is absolutely correct. That's 15 inches. That's better. Right? 15 inches. 2 feet, not 18. Excellent, excellent. Fixed. My bad. Okay, I had the 9 in my head. There we go. 6.5, 9, 15, 24. That all looks good. Okay, so now I'm going to say, let's see. I've got some variables here. I want to know about this length, and I want to know about, that was my x length, and I'm going to want to know about this, and I'm going to want to know about that. Okay, so I can set up some ratios just like Richard told me I should. What ratio can I set up? Anyone got a ratio in mind? I see that here and here is a corresponding side. So I know 2 sides of these similar triangles. And I've got this length and this length. I think I could figure out z. And I think if I know z, I'd have a right triangle with the side and another side. And I could get y. And I think if I knew y, I could get x, because I'd have this whole triangle. So I'm going to say, let's see, the ratio of the big triangle, 6.5, to the small triangle, 2.5, is equal to the whole hypotenuse of the big triangle, 24 plus z, over the hypotenuse of the small triangle, just z. Everyone follow what I did here. I said, in this big triangle, 6.5 is the height, and 24 plus z is the hypotenuse. And in this small triangle that I've added in, 2.5 is the height, and the hypotenuse is z. Is that reasonable to everyone?
Cool. Thank you, Lauren. Okay, so solving for z, I have 6.5 z equals 2.5 times 24. What's that? That's hard math. 48 and 12, 60. 60 plus 2.5 z. Thanks, Ryan. Minus 2.5 z. Six minus 2 is 4. 3z equals 60. Z equals 20. So now I know this entire length is 44. Jasmine said 4. Did I miss something, Jasmine? Four Z. 6 minus thank you. Thank you, thank you, thank you. Much appreciated, Michelle and Jasmine. 4Z, that's a problem. So Z should really equal 15, huh? Z should really be 15, which means I need to fix this over here. Z equal to 15. That's no good. And 24 and 15, 39. Is that all better? Thank you, Jasmine. Thank you, Michelle. Look at chat. Stop. Look at chat. Thank you, Oscar. Thank you. 39. Got it. Thank you, Oscar. Did I catch up with everyone? Are we all there? We're all at 39. You know, caught my mistake. Much appreciated. Cool. Okay, so now I know this whole length, 39. Should we solve for x? I think it's time to get x. So we're going to say that the ratio of the big triangle and the ratio to the small triangle. So let's see. Whole triangle has side x plus y. We got hypotenuse, hypotenuse. We just need the base. So to get this entire length, I'm going to say a squared plus b squared equals c squared. So 6.5 squared plus b squared equals 39 squared. And b squared equals 39 squared minus 6.5 squared. And b equals the square root of 39 squared minus 6.5 squared. And I'll stop doing math in my head because apparently I'm not very good at it, as you guys have now realized. So I'll go ahead and plug that in. Square root of 39 squared minus 6.5 squared. B equals 38.45. So this entire distance is 38.45. And let's see, in the little triangle down here, 2.5 squared plus y squared equals 15 squared. I know that a squared plus b squared equals c squared. So 2.5 squared plus
y squared equals 15 squared. Let's see. Square root of 15 squared minus 2.5 squared. 14.79. And x equals 38.45 minus 14.79. So x, oh no, minus. $23.66. Okay, hey, we made it. That was great. No, I just had a cough. My voice is getting a little sore from talking for like an hour and a half straight. But let's see, we got x. I'm going to leave this page. Did you all catch it? You maybe want to snap a shot on it or something like that? I don't know. You can go back and watch the video. You'll be fine. So I'm going to leave this page and come back here where we'd already developed these. We already broke down the problem into multiple parts where we said half circle, x, and another half circle. So we'd already gotten 9 pi plus 2x. So now we're taking x from this page of 23.66 and we're saying 9 pi plus 2 times 23.66 equals 9 pi plus 2 times 23.66, 75.59 feet. Yeah, Richard, this video it's on YouTube. It gets saved. You can watch it. You can watch it whenever you want. Let's see. We did the whole problem set. That was the review set. Should we? You guys wanted to talk about comparing and contrasting law sines, law cosines, Heron's law, right? I think so. Let me pull that up. So I think fourth period we didn't get to, but sixth period we did. So let's pull up sixth period's work and we can see if we want to add to it, we can. Just have not been saved. Sure, we'll save our review work. Review. Pre-calc midterm. And what was that? Trig. And actually, this whole file that I'm showing you now is online on my website. And so I can post it on your website. Yeah, this whole thing is there, and the whole thing I just did. So this is on my website already, and what I just did in this video is in the video, which you can watch later, and also the file I can put out. Yeah, the Venn diagram. Let's look at this. So a Venn diagram is a good way of comparing and contrasting. You don't have to use a Venn diagram, but I think it's nice. We want to be able to talk about what do all of these things have that are different, and And what brings them together? Oh, something broke. Let's see, using switch. And switch. There you go. Now I'm back. Yeah, Emily, I'm at school because the internet is here is a lot better than my internet at home. So I've done it from home before, but you guys you in the past people have told me in the past people have told me that when I do it from home, it's just like the lag is like really really bad. And already you guys are noticing that the lag is kind of bad. And Jasmine and Emily, the lights are off because if I don't stand up and move around, the lights automatically turn off. So I've been getting up and turning them off, but they just gone off. No, I didn't sneak into my own classroom, Brian. Here, I'll turn the lights back on. Well, whatever your name is, it's not in my class. You're welcome to come visit me after school. Anyway, let's talk about this compare contrast. So things that made all these different, we said were that Heron's law was for finding areas. We could have said, ooh, a good thing here is that we didn't add. For SSS triangles. So here was Heron's law in this triangle. This was law of cosines in this triangle. And this was law of sines in this circle. And we said Heron's law is for finding areas. We said these two, law of sines and law of cosines, is for finding sides and angles. We said that law of cosines is good when we need to solve side angle side situations or side 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 situations. And that in the law of cosines, we can get obtuse angles. Whereas law of sines, we can't get obtuse angles. And it has an ambiguous case, but it's helpful if we need side-side angle situation. That's the ambiguous case. Angle side angle, and angle angle side. Both Heron's law and the law of cosines needed the Pythagorean theorem to be proved, whereas law of sines did not. And then this centerpiece is real critical. What unites all three, and this is really what I want you to know on this material, is that all three are united by being, all of them were derived. We did the same thing in the proof to derive every single one. And what we did was we dropped an altitude, we drew the altitude in an oblique triangle, and we wrote a system of equations using right triangle information, be it Pythagorean theorem or sine or cosine. This is what brought together all of these situations. So yeah, that's one way you could do that compare contrast work. But that's what you need to be able to speak to. You need to be able to tell me what makes them all different and what makes them the same. Questions there? Jasmine, it's possible you might have to derive one or more of them.
I did make the guarantee that you would not have to derive Heron's law. That's too long. Not worth memorizing. Lauren says, "Are translations and dilations going to be on the test?" Yeah, there will. I think there will be dilations, but not rigid transformations. So we talk about dilations. Emily, that is absolutely correct. You can only get an ambiguous case with side-side angle with the law of sines. Brian said, "Is there a bonus question on the test?" What do you mean bonus question? We haven't done any bonus questions at all. Have you heard stories from last year, Brian? Is that what you're talking about? Richard, what are you writing? EC, yes. Cough, cough, we. Got it. Cough, cough, Tiffany. Got it. No, probably not going to be a bonus question. Bonus questions were something I did last year, but I got annoyed. Some people would spend more time on the bonus question than they would on the actual test, and it bothered me. So yeah, I dropped them this year. But yeah, I might bring one back for this test. It's possible. Anyway, dilations. Thank you, Lauren. What do we want to do? Do we want to just dilate some figures? We can do that. That's a good idea. Let's do that. So I had some kids in here doing that after school. And let me grab the practice problems we were doing. Who's Christine Williams? Oh, hi, Christine. I'm confused. Oh, well. Yeah, practice problems. All right, so let's see. Should we just practice some dilations? I think that's probably a good idea. Let's see how we're gonna let's do this one. This one's a tricky one. Let's start with that. So we're supposed to be doing a dilation about 0, 0. So here's the center of dilation. Center of dilation. And the scale factor is 3/4. Oh, I get it now. Christine Williams. Great. Oh, Emily, that's bad. Freezing isn't supposed to happen. Let's see. What do I need to do? How do I dilate it about the origin by a scale factor of 3/4? Anyone know? Richard says, how do we know that?
How do we know what we're supposed to do? Because it was in the problem. Find triangle PQR with a dilation of center 0, 0, and the scale factor which was given. Because it said it right here, 0, 0. That makes sense, Richard? Oh, good. Okay, cool. Great. Well, I'm not getting any help with this because Brennan is lacking. He would be find the coordinates of each point and multiply by 3/5, not 3/5, 3/4. 3/4. Thank you, Ryan. Yes. Yeah, we could do that. We can find the coordinates of each point and multiply by 3/4. Brilliant. Let's do that. So this point is, let's see, negative 3, 0. And so it's going to become negative 3 times 3/4 is negative 9/4. Whoops. Negative 3 times 3/4, comma 0, which is negative 9/4, 0, which is 2.25. So there's P prime. Great. And then this is going to be the same deal. So that's going to be Q prime. And it's at 0, 2.25. And this is P prime at right there. And then this point, 2.25. So this point is, R right now is at 1, negative 3. So it's going to go to 3/4, comma, negative 9/4. So 3/4 here, negative 9/4 there. R prime. So there's Q prime, R prime, and P prime. Sweet. We did it. There was a dilation. Everything shrunk towards the center. Do we want to do some more stuff with dilations, or are we good? Sweet. You guys feel good. I feel good. Oh, finding the point of dilation. Oh, cool. Yeah, let's talk about that. Sophia says one more. Yeah, let's do one more and we can talk about Ryan's question. So same thing over here, or let's do over here. So this one's scale factor. Scale factor, I'm going to do scale factor 3, sure. So here, I'm going to start at this point. I'm going to look at this one geometrically. If our scale isn't perfect, Oscar, would I dock points if our scale isn't perfect? Like if you're talking Oscar, I think you're asking me about like here. If you were like just estimating fractions, meh, probably not. Thank you, Oscar. Dilation, not dilation, please. Nice face, Emily. I love it. Over here, I want to dilate by a scale factor 3. I'm going to think about this one geometrically rather than algebraically. So I'm just going to say, here's my distance that P is from, this is the distance from the center to P, and I need to make that distance 3 times as long. So I'm going to do distance, distance, distance. So I went, here it is once, twice, 3 times. So this is some value x, and this whole distance this is some length x, and this whole distance is 3x. So all I did was make this point P prime 3 times as far away as it was. So this is my new point P prime. How do we find the center of dilation? Well, in general, I'm going to talk about how we do find it if we don't know it. But Owen, in this problem, they told us that the center was 0, 0. But I'm going to back up, and geometrically, we're going to see how do we find the center of dilation if we don't know it, but we see the dilation. So next up, we got R. So here's the distance from the origin to R. I'm going to go that same distance again. Distance again. And that same distance again. So again, x, or let's call it y, and then this is 3y, 3 times as long. So here's r prime. Yeah, I'm going to talk about that, Owen, once we've got it done. R prime. And then lastly, I've got this distance from the origin to Q. Brian's been enlightened. Good to hear. And let's see, let's split that out, ungroup, and let's go ahead and duplicate that once and a second one. So 1 time, 2 times. So again, I took Q and I'm bringing it, making the distance from the center to Q 3 times as long, and there's Q prime. So here's my new triangle. With side Q prime, P prime, and another side over here from Q prime to R prime, and a last side down here, P prime to R prime. So doing this work geometrically answers the question that both Ryan and Owen had about how do I see the center of dilation. And the answer to that question is if I connect corresponding points in my image and pre-image, they're all going to meet back here at the center of dilation. So a straight line connecting any of them always meets at the center of dilation. So if I draw this line, you can see this line between Q prime to Q crosses the center of dilation, and this line from P prime to P crosses the center of dilation, and this line from R prime to R also crosses the center of dilation. Center of dilation. So if we don't know the center and we want to find it, we connect the points and we're going to find it. Oscar says, would you like coordinate points for 15? Sure, we can get coordinate points. It's a good idea. This was 2, 4. So symbolically, Oscar, the reason I don't have coordinate points is because I wanted to show it to you geometrically without a coordinate plane. Oh, and that's exactly correct, like the solving similar triangles. Similar triangles are the result of a dilation. So that was actually a dilation problem. So Oscar, if I want coordinates, that's 6, 12, because everything gets multiplied by 3. And over here, this was for 1, and it becomes 12, 3 when I multiply everything by 3. Oh, -1, -3. And over here, this was 2, -1. So it becomes 6, -3. Cool. All right. We're right on time. 5 minutes to 9. I feel done. I'm excited for an exam tomorrow. It'll be lots of fun. Emily, that is only for the specific case where we're doing a dilation about the origin. But yes, in the case where we're doing a dilation about the origin, then both coordinates x, y get multiplied by the scale factor. That is correct. I don't know who Luis Romo is. Do I have an Luis in pre-calc? Everyone loves my idea of fun. You guys are wrong. You just don't know what's fun. Yeah, exactly, Emily. Only when we dilate about the origin is that true. Not in every case. Basically not in any other case. And Oscar, yes, I am going home. Richard, he's in 3rd period. You're right, I do have a Luis in 3rd period. Cool. Person who's not in my pre-calc class. Oscar, I am not sleeping in my classroom. And Richard, I agree. I am going to drive home safe, and I'm going to drive home now. This was fun, guys. I hope this was helpful. I don't think I'll get into a car accident, but if I do get into a car accident, I left your midterms right here on the desk, so the sub will be prepared to give you a fat test and not help you at all. You are welcome, Brennan. And yeah, you're welcome, Ryan. I hope it was helpful. I'll see you all tomorrow for a, you're welcome, Sonny, no problem. Yes, Owen, I would use the geometric version, precisely. Richard says, wait. Can I show you the test? Yeah, Richard, I'm holding it up in front of the computer right now. Oh, you can't see it? Uh-oh. I'm showing it to you right now. I don't know why you're not seeing it. It must be technical difficulties. Anyway, talk to you all soon. Hope you have a good night. Sleep well. Don't stay up too late studying, even though it's fun. Peace out.
Are you still here?
Yep, but I'm leaving.